Welcome, everybody. It gives me great pleasure to welcome you to this 13th lecture of the Summer School on Dynamic Deformation of Solids, sponsored by CREDS. This is the last of our 13 lectures, and we are very happy to welcome today Justin Wilkerson from Texas A&M University, who will be telling us about dynamic fracture. Justin Wilkerson is an assistant professor in engineering here at Texas A&M University. He received his PhD also in mechanical engineering from Johns Hopkins University. He has had a number of awards, but perhaps one of the ones that I would want to sort of draw attention to is that he was in 2016 awarded the AFOSR Young Investigator Award, which is quite an honor. His interests are in micromechanics, multi-scale modeling, impact mechanics, shock physics, and planetary science. So we're very happy to have you, Justin. I'm going to stop my sharing now and hand it over to you.
Great. Okay, so you should be able to see my PowerPoint slides, hopefully. All right, so I will go ahead and get started here. So I'll be talking about failure, fracture, and a little bit about fragmentation, not much about fragmentation, under dynamic loading. So I thought I would start by showing you a few cool videos from the Texas A&M Hypervelocity Impact Lab that's headed up by Professor Tom Lacey in mechanical engineering. And so this is a picture on the top right is a picture of the gas gun, two-stage light gas gun that we have at Texas A&M. It can fire projectiles ranging in diameter from 4 to 10 millimeters, impact velocities ranging from 2 to 8 kilometers per second. That's speeds of 4,500 miles per hour to 18,000 miles per hour. Or a simpler way to think about it, if you're in College Station, going from College Station to Houston in about a minute. We have some high-speed imaging capabilities there, like 10 million frame per second camera, and working on acquiring a flash X-ray system right now, as well as some diagnostics techniques. This is just a picture of the schematic of the gun and how it basically works. So you have a powder chamber down on the far left end, and you light gunpowder, which launches a plastic piston down this pump tube. That pump tube compresses a light gas, in our case this is hydrogen, to very high pressures. It breaks a diaphragm in the breech, and that launches the projectile package down the launch tube, and then there's a target in the target tank that we can strike. And then through these windows, we can image what's going on. So I have a couple videos here that'll hopefully kind of motivate the talk. So here's a projectile coming in from the left at 6.4 kilometers per second, and it's impacting a 1/8 inch thick, ultra-high molecular weight polyethylene plate. The projectile is a 4 millimeter aluminum alloy sphere. And you can see all the impact damage that's generated. We have both front face debris and back face debris that's created. The projectile penetrates through this target, obviously. You get lots of fragmentation. In this case, this polymer is failing in what appears to be a fairly brittle mode. You get lots of little fragments going out. We might be interested in the velocity of those fragments, the fragment fragment size histogram, as well as the angle at which those fragments come off. Next, I'm going to show a video of a fairly similar polymer from a molecular standpoint, but it's going to have an extremely different failure mode in this hypervelocity impact situation. So this is high density polyethylene impacted at very similar conditions, similar thickness, same projectile. Everything's pretty much the same, but you can see that we have in totally different failure mode. So here it looks more like a membrane-like failure, soap bubble type failure. It looks a lot more ductile. You see a lot more stretching and deformation. So the point I want to raise here is that subtle differences in the material composition or the material microstructure can really be amplified when it comes to dynamic failure of materials. And that will be a theme that will kind of be carried throughout this talk. Let me show one other video that I like. Is pretty cool. Again, this is coming from the Hypervelocity Impact Lab at Texas A&M. So this is a plate of PMMA, and on the back side is a ballistic gel. And so what I like about this is you can actually visually see the shock waves moving through the gel. And then when the shock waves bounce off the free surface, you'll be able to see them initiate tensile damage failure modes in the gel. So let me play that video. So here comes the projectile from the left. It impacts the PMMA. And then you can see these, oops, sorry, let me play that again. Okay, and then you're going to be able to see a fairly semi-hemispherical shock wave moving out. It's going to hit the boundaries and cause reflection waves that come off. Those reflection waves are going to take the material from a nominally compressive state into a tensile state. And when it goes into that tensile state, it causes cavitation of the gel. So void nucleation inside the gel. And so all these black splotches that you see showing up are cavities forming inside this ballistic gel. And so you can just see there's a lot of physics going on here. You get shockwave propagation, reflection, rarefaction fans, and damage, impact damage that's induced. Okay, so when you subject any material to high velocity impact, it has several mechanisms that it can go about dissipating that energy. And I'll walk through a few of those. So the first that you saw the most in those previous videos is impact ejecta and fragmentation. So you're getting ejecta both off the front face and ejecta off the back face of the target material. And then you tend to get lots of fragmentation, so the material breaking up into small pieces. If you hit these things at incredibly high velocities, you can get vaporization and melting. That's not going to be the focus of the talk here. We're going to stay at lower regimes where fragmentation and failure is the most interesting phenomenon. If the target material is brittle that you're fired into, then you'll tend to get brittle failure modes. And that typically consists of brittle cracking. You can have crack nucleation. You can have crack branching, where a single crack will split out into multiple cracks. And then you can have fragmentation as well, which we'll briefly talk about at the end of this talk. In a more ductile material, you have a couple common failure modes. One is adiabatic shear localization. So what's happening here is that this is primarily a shear-dominated loading, and you can see that the material is plastically flowing in a shear way, but it's localizing into a small band. And the reason that we tack on this word adiabatic here is because this localization is accelerated by heat. So if you start to get more plastic deformation in a single region, then that region will heat up more. There will be thermal softening in that region, which will make that part of the material weaker. And because it's weaker, you'll have even more deformation in that region of the material, and you kind of get a runaway effect. It tends to happen at high rates because at high rates, thermal conduction is pretty slow. It's not necessarily totally negligible, so this word adiabatic is not quite right. It should probably be quasi-adiabatic shear bands, but that's the terminology that we've had for a while. And so if you load the material slowly, then there's time for thermal conduction to take that heat away, and you don't have the instability forming, at least not as severely. again, I'm not going to talk too much about that failure mode today. What I'm going to talk mostly about here is actually SPAL failure. So this figure here in the top left is a really nice visualization of SPAL failure. So you had a aluminum projectile that comes from the top down, and it impacts this armor plate of aluminum as well. And when it does that, it impacts at 6.8 kilometers per second, so an incredibly high velocity. And the projectile burrows in and creates a crater, right? So it kind of looks like if you were to take a rock and throw it in a pond, you would get kind of a splash, and then it looks like that's frozen. But in fact, this is all just plastic deformation. There's very, very little melting that has occurred in this impact. I would say far less than 1% of the material melted in this situation. And so all of this is just due to the very, very high deviatoric stresses that are created from this impact that cause the solid material to flow like a liquid, even though it's still in its solid state. So it's plastically flowing, and it's creating that crater formation. In this case, the target material is actually thick enough that it stops the projectile. So the projectile burrows about halfway through the target material, but it doesn't penetrate. So in that sense, the projectile has stopped, or the target has stopped penetration. And if we think of this as an armor material, then it kind of did its job in that sense. But what it can't do is it cannot stop the shock waves that are generated by the projectile impacting the surface of the target material. So when that projectile hits the surface of the target material, it sends out shock waves, and those shock waves propagate through the target material. They bounce off the free surface as release waves, similar to that video that we just saw on the previous slide. And when those release waves come back, they can interact with one another and cause a zone of tension in the material. And that zone of tension is where we have all of our dynamic failure, dynamic fracture occurring. So in a typical ductile metal, what will happen is you will nucleate a bunch of voids in the material in this tensile zone. Those voids will grow, they'll coalesce, and they'll form a big crack. And then this is a kind of a special situation where this SPAL scab is what we call this piece down here, a SPAL scab. In this case, it did not break away, but typically that will break away, and it's actually, unfortunately, the main way that soldiers that are tank operators die in action. And so what you could do is you could try to double the thickness of this armor plate, and this SPAL failure can still occur. So if you really want to make the armor more resistant to this failure mode, you have to dive into the material microstructure and make the material microstructure itself inherently more resistant to that type of failure mode. So I have a quick video here I'll play from the National Geographic channel where a chemist kind of provides a real-world demonstration of SPAL, which is kind of interesting. So I'll let this play for a couple minutes.
To kill a tank crew, it doesn't even have to get through the armor. To demonstrate the deadly nature of this weapon, we've asked chemist and explosives designer Sidney Alford to set up an experiment.
So here we have 150 grams of plastic explosive.
Sidney has welded steel armor to a metal plate and bolted this in place on the side of a mock-up turret.
Target. Thus.
His challenge, to destroy the inside of the turret without penetrating the armor.
I'll plonk it a bit more.
This plastic explosive he's patting into place will replicate the behavior of the real squash head.
That now represents the explosive which has arrived inside a shell which has squashed itself against the target. See, detonator?
Inserting the detonator turns the harmless, inert putty into a lethal explosive that could blow most of the roof off a house. There's a melon sitting in for the crew.
Goodbye, melon. I say that. 3, 2, 1. Ah, here we are.
At first glance, it looks as though Sydney's squash head has failed to do its work.
And if you look round the back of the plate, I think I see one former melon, which is no more. And here, still warm. You would not like to share the inside of a tank with this travelling at, I would guess, roughly the speed of sound.
This scab of steel has been blasted off the inside of the armour.
What I'll do now is unbolt this and we can have a good look. There we are.
Okay, so the piece that he's holding is the spall scab that I was talking about.
To kill a tank crew, it doesn't even have to...
So the way that we study this this failure mode in the laboratory is through plate impact experiments. So through plate impact experiments, we can learn a lot about spall failure, which is important for that particular application, obviously. But in addition to that, it's just a very nice, controlled way to understand dynamic failure of materials in general. So it has the important application for soldiers, but in addition to that, it's just a really nice tool to understand the fundamental behavior of materials as they're failing on very fast timescales, or failing at extremely high rates. So let me walk you through a little bit of a plate impact experiment. So typically you'll have a target plate or a specimen plate, which is shown here, and then you will launch into it a flyer plate, and these are disc basically. And the flyer plate will come and it will impact the stationary target plate or the specimen plate. And when it does that, it will send a shockwave through the material. And typically we end up having our specimen plate or our target plate be roughly twice the thickness of the flyer plate. And you'll see why that is in a moment as I walk through this wave diagram. This simulation here in the middle is a simulation of an aluminum flyer plate material impacting a stationary magnesium target material. So aluminum flyer hitting magnesium. And so the aluminum has a density of 2,700 kilograms per meter squared, meters cubed, and magnesium is about 1,800 or so. So it comes up as red in the color scheme. And so when I press the animation forward, and typically we think about these in terms of a XT diagram, but let's just look at the simulation first. So right now, this is just showing what happens right before impact. So I'm going to click forward, and there's going to be a shockwave move through the target material. Okay, so you can see how the red colors, which are the ambient density of the magnesium, are converting to blue, which means that we're compressing the magnesium with a shockwave. So the interface between the red and the blue is the shock front propagating through that magnesium target material. This is actually a full 3D calculation, and so the shock front can develop whatever complex spatiotemporal form that it wants, but you can see that it's propagating in a nice one-dimensional fashion. Out towards the edge, there may be some edge effects, but for the most part, this looks really one-dimensional. Whatever's happening here is happening the same up here. So that's one of the things that we really like about plate impact experiments, is they're nice and one-dimensional, and then we can do some really simple one-dimensional analysis to back out what's going on in the material. It's not shown here in the visualization, but the stress state and the strain state are actually fairly simple as well, at least for isotropic material. So for an isotropic material, the strain state is uniaxial strain. So that means as the shockwave propagates through, the material is being squeezed in the longitudinal direction, the direction that the shockwave moves. And then there is no Poisson's contraction. in the lateral directions at all. Those stay fixed. Okay. And then as a result of that, there's a multi-axial stress state that's developed. So there's stress in this longitudinal direction, and then there's stresses in the lateral directions as well, because it's basically like a confinement. We don't allow the Poisson's contraction due to the timescales of the shock propagation. And so that's the stress state that you end up with. Okay, so since everything is pretty one-dimensional, we typically visualize these things in terms of XT diagrams, because there's only one spatial dimension that matters, which is the X direction, or this longitudinal horizontal direction. And then the time scale is what matters quite a bit. Okay, so on this XT diagram, the propagation of the shock front ends up looking like a line here. Okay, and the slope of this line is dictated by the wave speed of the material. And the wave speed of the material is a material property, which is basically the square root of the stiffness of the material divided by the density of the material. Okay, and so these shock waves are generated and they propagate out after the impact occurs. One propagates into the flyer plate and one propagates into the stationary target material. And when that shock wave hits the free surface, it causes a jump in the what we call the free surface velocity. So what we can do is to sit back here on the back face of the target material, and we can measure the velocity through the Doppler effect. Okay, so we hit this with some kind of laser, measure the red shift or the blue shift in the laser, and then through Doppler effect, you can determine the velocity of this free surface. So this free surface will, if we sit and watch what happens to the back free surface, it's moving with zero velocity, zero velocity, zero velocity, and then the shock wave hits, and then all of a sudden it accelerates away. It accelerates to the right. And so that shows up as this. What I'm plotting here is the free surface velocity, which is typically what we are measuring in the experiments as a function of time. Okay? And so that's measured from the back face in the XT diagram or from this back face in the simulation. So you get this jump and you come to this point B, relates to point B here in the XT diagram. After that, I hold in a Hugoniot state for a little while. So I jump up to some velocity and the back face just moves at that constant velocity. And it will hold at that velocity until another wave interaction comes. So from point B to point C, nothing interesting will happen. The free surface velocity will just be fixed at some value. What happens at point C is the first wave interaction is arriving. So there was a shock wave that moved from the contact surface. It goes to the front face of the flyer plate. It bounces off as a release wave. The reason that they become release waves is essentially you have this material, the flyer plate is in a highly compressed state after that shock wave moves through. But then when the wave gets to the free surface, it realizes what the boundary condition is. And this is a traction-free boundary condition. So if I have a traction-free boundary condition over here, why am I in this highly stressed state? So then it uses that information to send a release wave back to unload the material. And so this is a release rarefaction fan that's coming back. And when it hits the back surface again, then we see a drop in the velocity. Okay, but before that wave goes all the way to the back surface, there's actually another interaction in the spall plane. So I got a release wave coming from the left. In addition to that, I have a release wave coming from the right, which is coming from the back face of the target plate. And those two release waves are coming to each other right in the middle of the specimen, which is where I'm going to form the spall plane. So I have a release wave that's trying to take me from highly compressed state down to zero stress, coming from the left. And then I have another release wave coming from the right that's trying to take me from highly compressed state back to zero stress. And when those two collide, they essentially release each other and they take you into a tensile state. And so rather than going to zero stress, you actually go to a highly tensile stress state. And that's where we get all of our damage in the material. So if I click through again, you can see in the simulation, I get the formation of this this yellow region, which is a low density region, which is an indication that I've nucleated a bunch of voids or cracks or something like that, some kind of damage in the spall plane of the material. And then that's going to cause some implications over here in the free surface velocity history. Okay, so again, this is our main diagnostics measure here, is free surface velocity versus time. So from that, we can back out a few things that tell us what was going on to the material before it failed and as it was failing. So one of the key metrics that we're most interested in is the so-called spall strength. And the spall strength is an indication of the maximum hydrostatic tensile stress or the maximum longitudinal tensile stress that the material sustained before it failed. Okay, and the way that we calculate that from this free surface velocity history is 1/2 the mass density of the material times the bulk wave speed times the difference in these two velocities that are measured on the back face. The velocity at time b, which is this velocity here, minus the velocity at time d, which is this velocity at the bottom of the trough before you start increasing again. Okay. In addition to that, a very important metric is the shock stress, which is the basically the magnitude of the compressive stress that the shock wave induced when it first propagated through the material. The reason that that's important is because that is essentially going to cause microstructure evolution when the shock first goes by. It's going to generate a bunch of dislocations. It may heat up the material. It will heat up the material a bit. If the shock stress is high, it can heat up the material quite a bit. And so essentially you have by the time spall failure occurs, you have a material that's gone through a compressive cycle first. And so it's a totally different material than it was in its pristine condition. So you have to take that into consideration. And so we always want to report and know what the shock stress was in a spall experiment. And then the last one that is really important is the tensile strain rate. Okay, so this is the average strain rate that the material experiences in the spall plane as it's ripping itself apart. So as this yellow damage region is forming, what is the strain rate that's pulling that crack open? And that's calculated here, or it's roughly approximated as 1/2 the inverse of the wave speed, and then we take, we're basically looking for this slope here. So we take the difference between velocity at C and velocity at D and subtract out the time at C minus the time at D. And that will tell us roughly the strain rate that the material was experiencing. And so we can vary a number of conditions to study spall strength under different conditions. So obviously we can launch the flyer plate at different velocities, and higher velocities are going to generate higher and higher shock stresses. So that's the main way that we control shock stress if we want to understand how shock stress affects spall strength. The main way that we control strain rate is actually through the thickness of the flyer plate material itself, or the flyer plate target. So if we make the flyer plate target smaller, what that does is it allows less time for these rarefaction fans to spread out. And when they stay more compact, then you go from that highly compressed state to the highly tensile state faster. Okay, so this rarefaction fan is basically the time over which you go from the highly compressed state to the tensile state. So a thinner flyer plate is going to tend to give you a higher strain rate. So there's experiments that we can do with laser-driven flyer plates that are really foils, flyer-driven foils that are very, very thin, on the order of hundreds of microns. And then in that case, you can generate really, really high strain rates. Okay, so that's kind of all I want to talk about here as far as these XT diagrams and how we actually analyze the real experiments. Moving forward, we're just going to think about how spall strength is affected by shock stress, the tensile strain rate, and microstructure. Okay, so let's take a look at some experimental observations. So I'm going to plot that tensile strain rate that you experience in the spall plane as it's ripping itself apart on the x-axis. And then I'm going to plot spall strength here on the y-axis. And then we carry out a number of experiments on aluminum. This is a pretty ordinary aluminum, nothing special about it. But what you can see is at really, really high strain rates, on the order of 10 to the 8 per second, this material can hold 6, 7, 8 gigapascals of tensile stress before it rips itself apart. It can only do that for a few nanoseconds, really. So strain rate of 10 to the 8 per second means that this material is going to completely fail in about a nanosecond or so. Okay. Or at least it'll get to 10% strain in about a nanosecond. And we have this incredibly strong rate sensitivity associated with spall strength. And so we want to understand what's the physics that really governs that. Can we model it? Can we control it from a material design standpoint? Just to give you an idea of where you would typically see these strain rates in applications, strain rates lower than 10 to the 4 are typically associated with automobile accidents. 10 to the 5 and 10 to the 6 would be what we would see in a lot of these defense applications, particularly like the tank application. 10 to the 6 and 10 to the 7 is what we would see in orbital debris impacting spacecraft and space shielding. So that would be another application of this research. And then 10 to the 7 and 10 to the 8 is what you would expect to see in laser-based weapons or laser-driven spall type failure. Or I have a joke, Johnny Manziel stiff arm. This is a dated joke, obviously. And so, can we predict and control this behavior is fundamentally what we're after. One thing that's probably the most interesting to me in working in this field is that when it comes to spall failure, the role of defects is complex and non-intuitive. It's not always straightforward, the way defects are going to play out. So one thing I'll show here is that grain boundaries tend to serve as void nucleation sites in spall failure. So you can see these. This is an EBSD image, so every color is a grain oriented in a different way, and the boundary between two different colors is a grain boundary. And so these black regions here are showing voids and damage that's nucleating primarily along grain boundaries. There is some voids nucleating in the interiors of large grains, but for the most part, it's mostly along grain boundaries. If you do a more thorough analysis of what's going on as far as damage along certain types of grain boundaries, what you find is that some grain boundaries are actually more susceptible to spall failure than other grain boundaries. So here we have the likelihood that any randomly selected grain boundary will have damage on it as a function of the misorientation angle of that grain boundary. And what you see is that for low angle grain boundaries, you tend to not have much damage. For intermediate grain boundary angles, you have the most likelihood of forming, so those are the most susceptible to spall failure. And then the high angle grain boundaries are the least susceptible to failure. This is biased by the fact that a lot of these high angle grain boundaries are actually sigma 3 twin boundaries in this particular experiment. Here's a spall experiment that was done on a bicrystal copper, which was pretty cool. So you have two crystals, and the shock comes from the bottom up. And on the left-hand side, you have a crystal in which its 100 principal direction, lattice direction, is aligned parallel to the shock direction. And then on the right, I have an angle that's tilted from that. Okay. And what you can see is that you get different damage in each grain. So over here in the 100 side, I have more voids, but they're smaller. And then here in the tilted case, I have fewer voids, but they're bigger. And then this middle region here is the grain boundary between those two bicrystals. So you can see you get the most damage along the grain boundary itself. Okay, and then voids tend to nucleate from, if they don't nucleate from grain boundaries, then they tend to nucleate from second phase particles. And those second phase particles can be quite complex. So this is a micro CT image of second phase particles in an aluminum alloy. And voids can nucleate from any one of these second phase particles. And so if you want to build a real physics-based model, then this would be the information that you'd have to import into that real physics-based model. You'd have to know things about the spacing distribution, the size distribution, and as well as the orientation distribution of these second phase particles. Okay, so what we want to do is to talk about how we would develop a physics-based framework or physics-based model to think about spall failure in both metals and brittle materials. So before we do that, let's just briefly review some of the deformation and failure mechanisms that typically occur in ductile metals at quasi-static loading. So here I have a little cartoon of a notched bar, and we're going to just pull that bar vertically. And what you see is first you get some Poisson's contraction as you elongate the bar. You elongate it further and you get even more. Maybe you get a little bit of necking. The necking starts to become more severe as you continue to pull. So you get more thinning in the middle of the specimen. And then finally, after I've applied a good amount of deformation under quasi-static situations, quasi-static uniaxial tension, let me say it's specialized to that scenario. It's in this fairly late stage where I first start getting nucleation of damage. So these black circles here are indicating when I'm starting to get void nucleation. So I nucleate a few voids, I continue to stretch the material, I nucleate a few more voids, and then finally those voids start to coalesce and they form a crack and the specimen breaks into two pieces at that point. Okay, I'm sure in the other lectures you guys have covered this, so I don't really need to talk about it here, but you know that dislocations are line defects in the crystallography and the crystal lattice, and those line defects are the primary carriers of plastic deformation in crystalline metals. As far as damage goes, I've been talking about voids quite a bit as voids being modes of damage, and voids actually grow through plastic deformation of the surrounding material. So you'll have a second phase particle in the material, you debond from that second phase particle, and then you have basically a hole or a void in the material, and then you grow that hole by plastically stretching the material around it. Okay, so this is a TEM image, and these white regions are showing regions of high dislocation density because I had a lot of plastic deformation around the void surface there. Okay, and so we already touched upon this, but this is just showing a typical quasi-static load displacement curve where you load elastically, you hit a yield point, you get some hardening, you come to an ultimate tensile strength of the material. When I'm at the ultimate tensile strength of the material under uniaxial loading, that ultimate tensile strengthening is all associated with necking and plasticity of the material. It's not even any damage at this point. So So ultimate tensile strength should really not be thought of as having anything to do with failure or fracture. So I keep loading past the ultimate tensile strength, and it's not until I get way out here that I first start getting a lot of damage nucleation. So I'm getting voids nucleating. At this point in the load displacement curve, I have even more voids. And then down here, I start getting a lot of coalescence, and the material is losing its load carrying capacity very rapidly as these voids start to link together and form a big crack in the material. And it loses all load carrying capacity when that crack runs all the way across the specimen, and you get this kind of cut cone type fracture. It's just a zoomed in picture of it. And like I already mentioned earlier, these voids tend to nucleate at some kind of other material defect, be that second phase particles or grain boundaries, triple junctions, something like that tends to be the void nucleation sites in most metals. And then this is showing a few different of the coalescence modes, ways that two voids can link up and lose load carrying capacity. So there's a lot of complexity that's going on in spall failure. One good thing that makes life a little bit easier is that coalescence is probably the one thing that's way more complicated to model under quasi-static loading conditions than under dynamic spall type loading conditions. So we tend to see, for the most part, voids staying fairly spherical at very high rates, and they just grow until they touch each other. So coalescence modeling doesn't seem to be as big a deal at very high rates as it is at low rates. So I'm going to give you kind of one perspective on modeling these materials under dynamic fracture. I'll just mention here briefly that there are many other ways that you could think about this. And it builds on earlier models, essentially. So one of the most popular models for ductile failure, quasi-static ductile failure of materials is the Gerson model, which was originated in 1977, mostly in the dissertation work of Gerson. More recently, we've been able to do more multi-scale modeling to provide some further insights to that. Crystal plasticity extensions, as well as adding more sophistication to the constitutive models of the matrix material itself, be that anisotropy of the matrix material, size or strain gradient plasticity effects in the matrix material, as well as dynamic growth effects associated with the matrix material. Okay, so with that kind of as a background, I'm going to move into talking about how we model, how do we model these dynamic failure, these dynamic fracture processes in both ductile materials and brittle materials. So obviously, if we want to do a phenomenological or an empirical model, then that's just curve fitting, essentially. So we could do curve fitting. I don't need to tell you about that. But if we want to develop a physics-based framework, I tend to think that there's three key ingredients that are most important. One is that the kinematics and the softening be governed by actual defect evolution. So you're thinking about populations of defects and their evolution. And that's what's given rise to both the softening and the kinematics. The inelastic strain, essentially. So we don't just have a nebulous idea of a damage scalar or a damage tensor that doesn't have any physical connection. Everything in the physics-based model should ideally be observable under the microscope. Going along those same lines, it's important to account for the microstructure of the material as well as populations of defects. So you're going to hear in these physics-based models, quite often you're going to hear things like, obviously things like average grain size. It gives you an idea of the spacing between grain boundaries. but you're going to hear quantities like densities quite a bit. So dislocation density, that gives me an idea of the average spacing between densities, or how many dislocations there are in a unit volume of material. In addition to that, we'll talk about the number of voids per unit volume, which is very similar to the dislocation density. And we'll try to keep track of the average spacing between these different defects and the consequences of that on the material response. And then lastly, we want our rate dependence of the material to be governed by the fundamental defect kinetics. So we want to understand the fundamental defect kinetics, and then we want to build in the rate dependence of the material from that fundamental defect kinetics. Okay, so we won't just have some, again, phenomenological or empirical rate sensitivity exponent or something like that. We will build it from the fundamental kinetics of the defects that carry that inelastic strain or inelastic deformation. Okay, so the first thing that we're going to talk about in this recipe is the kinetics of defects. Okay, so defect kinetics are important, like I said, because they govern the fundamental rate sensitivity. And so that's what we want to focus on first. So we're going to touch on kinetics. I'm going to briefly touch on the kinetics of many of the defects that you see in this diagram here. You see things like cracks, so we'll talk about crack speeds. You see things like voids, so we'll talk about void growth rates or void speeds. Dislocations, the rate at which dislocations move through the material. Vacancies, how fast vacancies diffuse and cluster together with one another. And then we can build all that together in our physics-based model. Okay, let's see. Yeah, in the interest of time, I will skip this video. Well, let me show one of them. Okay, I'm going to show this one video. Are you able to see this YouTube video?
Not yet.
Oh, not yet. Okay.
So we could see the screen on the YouTube. It just didn't look like it was moving.
Oh, you could.
Yeah, so we can see the screen and it just, there we go.
Okay. So this is a projectile impacting glass. The projectile is moving really fast, but the frame rate of the camera is 10 million frames per second. So it looks like this projectile is inching along. So that'll give you an idea of how much we have slowed down everything in this video. And then you can see these cracks nucleate underneath the impact spot, and then they propagate outwards. You get some radial cracks and some circumferential cracks. But the main thing I want you to take away from this is that they move at finite speeds. They're moving at very fast speeds, but they're finite. And because of that, that means that there's a finite rate at which the material can relax stresses. Okay, so that's actually why we get to such high tensile stresses in the Spall experiment, is because the damage just can't grow fast enough to relax the stresses. Okay, and as we talk about these things, we'll find that there are many upper limits on how fast different kinds of defects can grow. Okay, let me switch back to my PowerPoint. And then these guys from the slow-mo guys, they have a nice video of crack propagation through a plate. I have the link up here, which I'll share with you, but I won't play that here in the interest of time. Okay. And are we back on my PowerPoint slide? Are you seeing that?
Yes, sir.
Okay, perfect. So no more switches, so we should be good the rest of the talk. The first thing that I want to mention, let's first talk about the kinetics or the dynamics of cracks as they propagate through the material. So you saw that visualization in the last video. This is, on the left, is a typical kinetics diagram or dynamics diagram for the velocity at which dislocations can, or sorry, the velocity at which cracks can move. So on the x-axis, you have the so-called stress intensity factor, which is a measure of the stress state right at the tip of a crack. And on the y-axis, you have the velocity at which the crack will move under that applied stress intensity factor. Okay? And so what you find is that, and this is actually a log scale on the y-axis. And so when the stress intensity factor is low, you get a fairly linear line in log-log space, so it's a parallel relationship. And we call that stage 1 of the relationship between crack velocity and stress intensity factor. As you approach the K1C of the material, then the crack velocity shoots way up to very, very high velocities. Still fairly linear on this log-log plot. And then it tends to saturate out at an upper limit. And that saturation velocity is typically the Rayleigh wave speed of the material. Okay, the Rayleigh wave speed is the speed at which a surface wave will propagate along the surface of a material. So when you take a rock and throw it into a pond, you see the ripples moving out. They're moving at the Rayleigh wave speed of the material. And the reason that that's important for the propagation of cracks is because I need to, basically there's some far field stress that needs to get concentrated at the tip of the crack, right? And the cracks themselves are free surfaces, so the Rayleigh wave speed becomes really important. Okay, the Rayleigh wave speed in most materials is going to be on the order of 1,000, 2,000, 3,000 meters per second, somewhere in that ballpark. So that's going to be the fastest that cracks can propagate through a material. If you remember anything from fracture mechanics, there's formulas and tables by which we calculate stress intensity factor as a function of the geometry of the body, the geometry of the crack, and the applied stress state. Okay. One important thing to remember when it comes to fracture stress intensity factor is that it's a function of the crack size itself. So here I'm using L to denote the crack size, and S denotes the size of a flaw from which that crack nucleated. And so you can see here in this term here, I have that typical square root of the crack size dependence that we always see in the stress intensity factor. Okay, so as the crack grows, the stress intensity factor gets higher, and that's why brittle materials tend to be unstable and have an unstable failure mode, because you have a runaway instability. As they propagate, stress intensity factor just goes up, the crack moves even faster, and you just get fracture. The criterion for a crack to start growing is generally when the stress intensity factor is equal to a material property called the critical stress intensity factor, K1C, and then the dynamics of crack growth. So basically, this curve here, we measure the velocity of those cracks in experiments, and then we fit a relationship to that. And so this is the relationship that's most often used. Out here in the prefactor, you have the Rayleigh wave speed, and so that's going to be the upper limit. As you go to very, very high stress intensity factors, you're never going to drive this any faster than the Rayleigh wave speed. This alpha parameter can be used to drop that maximum velocity down a little bit if you'd like. if that's what your material exhibits. And then here we have the function of this stress intensity factor, which kind of gives us this curve as it approaches the asymptote. Okay. From a continuum mechanics standpoint, as you're deriving these kind of elastodynamic relationships, cracks and dislocations look fairly similar. They're both this planar defects in a material. And so from that standpoint, you get solutions that look pretty similar as far as the stress fields around either a dislocation or a crack. And their dynamics are somewhat similar, fairly similar. So next I'll show the kinetics of a dislocation, and it's generally going to be pretty similar. So the main thing that's different is when we're talking about cracks, we always talk about stress intensity factors, which is a measure of the stress at the crack tip. And for every other kind of defect that we're going to analyze, we tend to think about the far field stress or the macroscopic stress on the material, or resolved shear stress on the plane, on the slip plane itself. So here on the x-axis, I have the resolved shear stress that's applied to the material, and then on the y-axis, you'll have the velocity at which the dislocation propagates. And so you can see some fairly similar trends. Again, I get a fairly linear relationship on a log-log plot for the kinetics of dislocations, and then that tends to turn over and asymptote towards the upper bound, which for dislocations is the shear wave speed of the material, tends to be the upper bound at which dislocations can propagate. For both dislocations and cracks, there are some special situations where you can have supersonic cracks or supersonic dislocation motion. So for supersonic cracks, there's some really nice work that was done by Eros Rousakis, as well as Weijing Gao and Marcus Buehler, where they showed how you can have supersonic cracks, and also the implications of supersonic cracks on earthquakes, how you can have a more devastating earthquake if the fault tends to propagate supersonically. And here by supersonic, we mean for cracks, speeds that are higher than the Rayleigh wave speed, or for dislocations, dislocation motion that is higher than the shear wave speed of the material. So both of those have been observed, especially in molecular dynamics calculations. So anyways, coming back to our kinetics law here, we have a fairly simple kinetics law that captures this linear regime. So when the dislocation velocity is small, we have a fairly linear relationship between the applied shear stress and the dislocation velocity. And the slope here is given as the dislocation drag coefficient. And then we asymptote towards the wave speed, and that asymptote is accomplished by this denominator here, this 1 minus dislocation velocity over shear wave speed squared. That basically causes the right-hand term to blow up as the velocity approaches the shear wave speed. So to drive a dislocation at speeds that are that's close to the shear wave speed, it requires an infinite amount of shear stress. So that's that upper limit on that. And then these mobility relationships are actually really convenient to characterize through molecular dynamics calculations. So in this case, we characterize this drag coefficient, B0, as a function of temperature and as a function of the concentration of solute atoms in a magnesium aluminum alloy. And that's a pretty straightforward use of multi-scale modeling in that case. Kind of continuing along this vein, I'm going to talk about the kinetics of twins very briefly, and it's very much a marriage of the kinetics of dislocations. So in this work, we considered a twin, right? And a twin is just a special type of a planar defect. You can think of it almost like a special type of a grain boundary, where on either side of the twin boundary, you have a mirror image of the crystal. Okay, and the way that a twin can move through a material is there's a couple of mechanisms that are hypothesized or observed. One is just a shuffling mechanism in which the atoms just shuffle themselves in a different way to facilitate the motion of the twin boundary. Most likely that probably requires quite a bit of stress for that to occur. A simpler mechanism is that there is a so-called twinning partial dislocation on the twin boundary itself, and you can just move that twinning partial dislocation along the twin boundary, and that's going to facilitate the motion of the twin boundary itself. Okay, so then what you end up getting is that the motion of the twin boundary, its kinetics, are just governed by the kinetics of the twinning partial dislocation and then the spacing of twinning partial dislocations along the twin boundary itself. And so we did some MD calculations and found that that exactly works. That idea works until you apply so much stress that you're nucleating new twinning partial dislocations. Then that idea kind of falls apart at that point. That's going to be another theme that we're going to talk about later, is that the spacing of defects and the evolution of the spacing of defects is one of the more difficult things to capture in these physics-based frameworks. Okay, so last defect I'm going to talk about as far as kinetics go is the kinetics of voids. So the question is, we've talked about how fast cracks grow, how fast dislocations propagate, how fast twin boundaries move, and now we'll talk about voids, how fast voids grow. So again, there's going to be this linkage to the kinetics of dislocations, because as I mentioned earlier, the way the void grows is by plastic deformation of the surrounding matrix material around the void. Okay, so if I want to grow a void very fast, I have to drive dislocations to move at very fast rates, right? But they're limited at how fast they can move. They can't move any faster than the shear wave speed. So that's going to put an upper limit on how fast voids can grow. In addition to that, something that's fairly unique to voids that we have to consider is there's an inertial constraint. So as I try to grow this void at a very fast rate, there's all this mass that's around the material, and I'm pushing that mass away radially. And there's an inertial resistance to that. If I try to accelerate that mass away at a very rapid acceleration rate, then there's an inertial resistance to that. That's going to work against that, and that's going to slow the dynamics or the kinetics of that, the growth of that void. Okay, so kind of the simplest way that we can model that is by first considering the balance of radial momentum of a spherical shell, which is given by this equation here. You have rho being the mass density, r being the radial coordinate, sigma r being the radial stress, and sigma theta theta being the hoop stress. And so sigma theta theta minus sigma r for a spherically symmetric problem is just the von Mises stress, or the deviatoric stress. Okay. And if I take that balance of radial momentum equation and I integrate through the thickness of the spherical shell, so start out at r equals a and integrate from this surface out to the outer surface, and then apply my boundary conditions. So when I integrate this derivative of the radial stress here, integrate that with respect to r, that's the integral of a derivative, so then it's just going to be the radial stress itself, which is then going to become the boundary conditions, which is the applied pressure at the outer surface, and if there's any Laplace pressure due to surface tension at the inner radius of the void. So I end up with this really simple integral differential equation that governs the dynamics of voids. So on the left-hand side, I have the far field applied pressure, and then on the right-hand side, I have 4 terms. One is the associated with the surface energy of the material. This is basically the Laplace pressure. So 2 gamma over A, essentially. This is only going to be important for really small voids. Then I have this microinertial term, which governs which essentially accounts for the inertial resistance. So as I have this mass around the void and I want to accelerate that away, there's a resistance to that, so that's accounted for in this term. It's essentially this rho r double dot integrated. And then I have 2 terms which come from the integration of this last term in the balance of radial momentum. And like I said, that is the deviant torque stress there. So those account for the resistance to void growth due to the resistance to plastic deformation of the matrix material around it. Okay, and so we split that term into 2 components, one associated with the quasi-static strength of the material. So what kind of far field pressure do you have to apply just to get the dislocations to start moving? And then a dynamic strength term, which accounts for the fact that I'm going to drive these at very high velocities, these dislocations, so there's going to be an overstress that's needed to propagate them at a high rate. Okay. And so that's essentially the rate sensitivity of the matrix material. So for those last 2 terms, I need to choose a plasticity model that's appropriate for the matrix material deforming at these incredibly high strain rates. And so for that, we make use of this dislocation-based viscoplasticity model of Austin and McDowell. It has multiplicative decomposition of the deformation gradient tensor into an elastic and a plastic component. The rate of plastic deformation is given by the tensorial form of Orban's equation. On the right-hand side, I have B representing the Burgers vector, Nm being the mobile dislocation density, so the density of mobile dislocations in the material, and then V being the average dislocation velocity in the material. S prime here is the deviant torque stress tensor, and then it's just normalized by a scalar von Mises stress. In addition to that, we have a hardening relationship, Taylor hardening equation, which dictates the hardening of the material. So as I increase both my mobile dislocation density and my immobile dislocation density, then the material will harden. So mobile, we'll make a distinction here that mobile dislocations are the carriers of plasticity. They're the ones that can move and they create plastic deformation. Immobile do 2 things. They can be barriers to the motion of mobile dislocations, so they create obstacles. And then in addition to that, they contribute to the hardening of the material. And then this is where we bring in the kinetics law for the rate at which dislocations propagate, according to this relativistic equation. And then finally, we need to have an evolution equation for how the dislocation density evolves with deformation. So we account for several mechanisms of dislocation density evolution. You can have nucleation of new dislocation segments. You can have multiplication of dislocation segments. You can have 2 opposite signed dislocations come and annihilate one another. And then you can have trapping as well, where a dislocation will run, a mobile dislocation density will run up against an obstacle where it'll get stopped and become immobilized. So then it moves to the immobile population. And we have a similar evolution equations that track the evolution of the immobile dislocation density as well. So all that's kind of needed to be able to model the kinetics of voids themselves. Okay, so I put all of that into the spatio-integral differential equation and solve that equation, and then out comes the kinetics of voids. So here I'm going to show 3 different voids of 3 different initial sizes, 10 nanometers, 100 nanometers, and 1 micron, and then show how their velocity evolves as the void grows. Okay, so the x-axis here is showing you the current void size as the void grows with time, and then the y-axis is the velocity at which it's growing. So what you find for very small voids is that their kinetics are dictated totally by the upper limit on the dislocation velocity. So what happens is you have very unstable stress situation for the dislocations around the void surface, especially in SPAL. And you right away, because void growth is fairly unstable, you drive these dislocations at the fastest rate that they can possibly go, which is the shear wave speed of the material. And then that creates the upper limit on how fast these voids can grow. So the voids are limited by this inequality here, the void rate, which tells you how fast they can grow. So basically 1/3 of the current void size times the Burgers vector times the mobile dislocation density times the shear wave speed. That's how fast they can move. They can't move any faster than that. Okay. And that has some similarities to the propagation of the twin boundary. Remember, for twin boundaries, they couldn't move any faster than the shear wave speed, and then there was a spacing of the twinning partial dislocations that came into play. So here it's the spacing of the mobile dislocations that come into play, the shear wave speed, and then what's different about voids is as they grow, they're able to move to grow even faster, which again adds to that instability. Micron-sized voids, the situation is a little different. Their kinetics are actually governed by that inertial resistance that we talked about earlier. So the fact that as you grow these voids, you have to accelerate mass away, out of the way, that becomes the primary constraint for the dynamics of micron-sized voids. Okay, and then we have a simple kinetics law that governs that. Okay. And then I have some more general solutions in some subsequent papers. So, and what's really important, like I mentioned already, is that the fact that these voids grow at very finite rates, so you can see here, this void, its maximum size or maximum void velocity is about 400 meters per second for this particular material with this particular density and for this particular loading state. And so it can't grow any faster than that. And so that's going to put some upper limit on how fast damage can evolve, which is going to put an upper limit on how fast damage can relax the stresses. If you can't relax the stresses, then the stresses just continue to climb, and that's how you get to these really high SPAL strengths that we were observing experimentally earlier. Okay, I will skip this. We also have kinetics laws for vacancies clustering into little nanovoids, but I will skip that in the interest of time. So the next thing that I want to touch on here is this component of kinematics and softening being governed by defect evolution. And I think this will be the last part that I'll dive deep into, and then we'll breeze through the rest of it a little quicker. So again, we wanted our kinematics and our softening to be governed by the fundamental defect evolution. So here, what we have to think about is that there are populations of defects in the material that are inducing the damage. Okay, so for ductile materials, that's primarily voids, like you see over here on the right. and voids that I have in this mesoscale cartoon. And so I have distributions of voids that are nucleating and growing, and they're all working together to soften the material. In a brittle material, it'll be the same story, but it's with cracks. And so I will nucleate lots of cracks. The main thing that will be different in brittle materials is those cracks are highly oriented. And so there's quite a bit of anisotropy that's introduced, whereas for voids, especially in spall failure, the voids are fairly spherical. So the situation is a lot more isotropic. Okay, so like I mentioned, so voids create a porosity. So porosity is what we'll denote that as phi here, and that's just the void volume fraction. So the number of voids that I have per unit volume of material multiplied by the total volume of all those voids, okay, which is taken care of by this integral in 4/3 pi. Okay, and so that gives me a net porosity in the material, and that net porosity in the material does a few things. One is that it degrades the elastic constants of the material, and so we can model that degradation of the elastic constants through mean field micromechanics, Eshelby type micromechanics. So in this case, we're using a Mori-Tanaka method to calculate the damaged stiffness tensor, and when you compare the Mori-Tanaka method with direct numerical simulations, it's extremely accurate in this case. For cracks, it's a little more complicated because the cracks have really well-defined orientations to them, like I mentioned, and so that can introduce quite a bit of anisotropy that needs to be captured. So one way that this is done quite well is in the model of Guangli Hu, which is published in JMPS in 2015. So I'll refer you to that paper if you want some more details on this. But essentially, they consider multiple crack families in a material, and a crack family is any cracks that that have the same orientation. Okay, and this vector n denotes the orientation of a particular crack family. And then they define an anisotropic tensorial damage tensor that basically sums up all of the crack volume associated with all of those cracks and then divides it by material. But it's a tensor because it accounts for the orientation of each of these crack families. Okay, so in here is the orientation vector for each family. S is the flaw size of the material, and eta is the flaw density in the material. So when you carry out this operation and you sum over all these parts, then you get a damage tensor, and then that damage tensor will create an anisotropic softening of the material. So this is an increase in the compliance of the material due to that anisotropic damage that's formed. Okay. One other thing that we have to account for in ductile metals that's not as important in brittle materials. In ductile metals, as we grow this porosity, yes, the porosity degrades the elastic constants, and we want to account for that, but that's not the most important thing. The most important thing is that the porosity degrades the strength of the material. So as I have this porosity in there, it just makes it easier to deform the material plastically, regardless of the stress state. The ease at which it's able to, the ease at which the resistance to inelastic deformation depends on the particular stress state. So typically we will make use of some type of yield surface to account for that. So the one that we make use of the most is similar in nature. It comes from the family of the Gerson type models, which you could call an I1 J2 yield surface. So it depends on the von Mises stress, or J2, and it depends on the mean hydrostatic pressure, or I1, of the stress tensor. So those two stress invariants become the most important. And And then the softening of the material as a function of porosity is accounted for through these yield surfaces here. Okay, so on the y-axis I have the maximum von Mises stress that you can apply to this material before it will start inelastically deforming. And then on the horizontal axis, I have the maximum mean or hydrostatic stress that you can apply before this will start to inelastically deform. And then you can see how these curves depend on the porosity itself. So if I'm inside these curves, then I'm elastically deforming. If I'm on the outside of those curves, then I'm inelastically deforming the material. And then we can build out more sophisticated versions of this for crystal plasticity. And then just to make the connection again, the last point I want to make is that the kinematics are actually really important when it comes to dynamic deformation of materials. So many constitutive models for quasi-static failure of materials, they will account for these first two aspects, that the elastic constants are degraded by damage and that the strength of the material is degraded by damage. But they won't often be as careful with the kinematics. So as you grow voids, then you are introducing inelastic volumetric strain into the material, and that needs to be accounted for. That's going to affect your wave propagation. That's going to affect all of this elastic volumetric strain energy that you had stored up in the material. You're going to relax the stress by converting that to inelastic strain. And that's not always accounted for as properly as it should be, but it's really, really important to account for this in dynamic fracture of materials. Okay, so I won't go through that anymore than to say that this is what we use for the kinematics for porosity. So you have this isotropic damage tensor that's created, and then for a brittle material, it ends up becoming an anisotropic damage tensor. And then a brittle material can still have lattice slip type plasticity as well, if you want to account for that. Okay. I think I will just take these couple more slides and then maybe stop. I don't want to go past an hour and a half. So now that we have that framework built up, we can use that. We can validate it against direct numerical simulations. So the framework has accounted for the kinematics of softening being governed by defect evolution. So we talked about how in a physics-based way, the porosity softens the elastic constants. In a physics-based way, it degrades the strength of the material. And in a physics-based way, we're able to convert elastic strain or elastic deformation, elastic strain into inelastic strain in a physics-based manner. And then we have all of our kinetics of defects, kinetics of dislocations, kinetics of voids being accounted for in a physics-based manner. We can throw all of that into a framework, and then we can compare with some direct numerical simulations that resolve voids explicitly. So here on the left, I have a DNS calculation where we're growing a void in a single crystal of copper. And so we apply a very high strain rate on the outer boundaries, and this void will grow. The contour plots are showing you dislocation density. So you can see that it's fairly spherically symmetric. There's a little bit of non-spherical symmetry due to the anisotropic crystal, but it's not a ton. And then we have this homogenized framework that we've discussed earlier, and then we can compare the two. So here in the bottom left is the evolution of the mean stress measured at the boundaries of the DNS calculation as a function of porosity, as the porosity is evolving. So what you see is you first elastically deform, then you start growing the void, and then you reach a peak. That peak stress would be like the Spall strength under that particular loading situation. And then as I continue to grow the porosity, then I get a relaxation of the stress. And then we do a fun thing out here at 15 or at 1.5% porosity, where we actually change the strain rate dynamically. So we were moving along at a strain rate of 10 to the 5, come up to this peak, and then come down. And then all of a sudden here, we increase the strain rate by an order of magnitude up to 10 to the 6. And then what you'll see is a jump in the stress. It comes back to a peak, and then it falls down due to relaxation. So this extra stress that we got, that was all a strain rate effect. And it's all coming from this physics-based framework that we've built. So that's the dynamics of the void itself is what's giving you this extra stress. So you increase the strain rate, and the void tries to grow faster, but it can't grow fast enough to relax the stress rapid enough. So you get a very high jump in the stress. So the fact that the physics-based framework can capture such a complicated loading situation is good. And I'll skip this. And then the physics-based framework is just more efficient as well. We also have some validation against MD calculations. So the lines here are MD simulations in a single crystal copper with voids of size 2.2 nanometers, spaced equally 22 nanometers apart. And sorry, the symbols are the MD calculations, and the lines are our predictions from the continuum theory, the physics-based continuum theory, and you can see that we capture the rate sensitivity very well, and we capture the softening well as well. And we can capture temperature evolution as well. So far I've just showed validation of the physics-based framework against more high fidelity simulations, be that MD or direct numerical simulations. The last thing that I could touch on, but I don't think we have time, would be comparison with experiments. So I'll just mention that the thing that's the most difficult in getting the model to agree well with the experiments is your lack of knowledge about the microstructure, lack of sufficient knowledge about the microstructure in the populations of defects in the material. So we have this nice physics-based framework, but I don't know exactly where the voids are going to nucleate. I don't know exactly how far they're spaced apart. I don't know what their initial size is going to be, what the size of the second phase particles are that they nucleate from. I don't necessarily always know the dislocation density on every slip system. What fraction of that dislocation density is mobile? What fraction is immobile? So those initial conditions kind of become the most difficult aspect in comparing with experiments. So I'll skip through, how we do that, but at the end of the day, we are able to get a fairly good agreement between experiments and the calculations. So these symbols in here are all experimental measures, and then the background contour plot is our theoretical and computational predictions. And so when the colors agree, that means that there's a good agreement between experiment and model. These square data points over here are from molecular dynamics calculations, and these are single crystal SPAL experiments on the right. And what this is showing is how SPAL strength depends on grain size in this really strange, anomalous way. It's very non-monotonic, as you can see here. So if you follow one color, that's a single strain rate. So let's just follow this cayenne color here. In that case, you would see that you get the lowest SPAL strength at this grain size of 5 microns or so. And if I increase the grain size from there, I would get an enhancement of the SPAL strength. The SPAL strength goes up. So something like reverse of Hall patch effect. And if I go to the left from that bottom trough, then I get an increase in SPAL strength, something like the Hall patch effect. Okay. And so this is a competition that's going on where as I decrease the grain size of the material, I make it harder to grow voids because the material is just stronger due to Hall patch strengthening. But because grain boundaries are void nucleation sites, I have more places to nucleate voids. And so there's a competition there in terms of whether decreasing grain size will enhance or degrade spell strength. And skip this. The last, I'll just briefly say for fragmentation, fragmentation is really about a competition between elastic wave propagation causing release waves to release a material point before it gets to fracture. So I don't think I have time to do this justice, but essentially just think about the fact that as you're loading, let's say that we're expanding this ring here, and we're expanding it outwards at some constant velocity. And so every material point just knows that it needs to be stretching and expanding out radially at some constant rate. And then all of a sudden, some point far to the right of you fails. Well, you don't know that that point failed until an elastic release wave propagates over to you and tells you that it failed. And so when that wave comes to you and tells you that it failed, then you will change your loading condition. But until that happens, you will not change your loading condition. So you will continue at that same strain rate until you get that information. So if that guy fails a few microseconds ago and you don't get the information in time, you're going to keep stretching and stretching, and then you may fail as you reach your local failure condition at that point. And so that's kind of the idea of fragmentation, and that's why you tend to get smaller and smaller fragments as you load a material at faster and faster rates, because the speed at which that information comes to you about the release is fixed. That doesn't depend on the loading rate. And so if you're loading very, very fast, then you're going to take more of the points to their failure before they receive that release information. And there's nice sophisticated computational methods to model fragmentation using dynamically inserted cohesive zone elements or using particle methods. And then there's some analytic methods that really came after, were really motivated during World War II, and a lot of those analytic methods were developed in World War II. Okay, so I think I'll stop there.
Okay, thank you so much, Justin, for this great and comprehensive talk. We have some time for questions. So following previous MO, please type your questions into the chat box and I will read them out loud for Justin to answer. So the first question that we're getting here is from Bob Hackenberg from Los Alamos. The question is, you said porosity degrades the strength of the material. Is this a reduced load-bearing area effect, aka geometric softening, or something intrinsic to the mechanics of solid plus void microstructures?
Yeah, that's a really good question. Yeah, so I should have probably stated that a little carefully, a little more carefully. I meant that from a macroscopic standpoint, if you think about a homogenized material, so essentially we're trying to build a homogenized model for a porous material. And so in that sense, the porosity does a few things. One, it does just create a geometric softening that you're mentioning. There's just holes in the material has less density, so it's going to lose some of its load carrying capacity. But in addition to that, it perturbs the microscopic stress fields. So the voids themselves, you can think about as being little stress concentration factors. And so the stress state around the void surface is a little higher than it is away from the void surface. It's a little easier to plastically deform the material around the void surface than it is far away from the void surface. So that also creates a softening at the macro scale of this homogenized material. Hopefully that answered the question.
Our next question is from Jinho Hyun. A brief question about ballistic impact experimental setup. Can we collect ejectas which fly on both impact side and propagation side? Chemical or physical changes on ejecta may be different from ejection angle.
Yeah, that's a good question. Yeah, so we call that soft recovery. Soft recovery is what you want, ideally, right? You can always go and collect the fragments that are laying around in the target chamber, but they're most likely they flew and they hit a wall somewhere in the target tank, which caused another impact event, which caused additional deformation. So what you're looking at when you collect a fragment just from the bottom of the target plate is a material that experienced multiple impacts, right? It experienced the impact conditions from the projectile, and then itself flew and hit something inside the target wall. So what you would prefer to do is to somehow catch those fragments, and that can be done. There's various recovery mechanisms. You could have the fragments go into some soft gel or some kind of soft material that hopefully doesn't provide any additional deformation of those fragments. But yeah, I agree with you that there definitely could, and most likely are, differences in the fragments that are formed from the front side versus the back side. And then there are also differences just in the spatial location where the fragments come from. So do the fragments come from right underneath the projectile or come from farther away from the projectile? All of that is always interesting to study.
I have a quick question. So in one of your descriptions, you were saying that the effect of capillarity or surface tension can be ignored for all but the smallest voids.
Yeah.
Do you know how small a void has to be before capillarity begins to play an important role in fracture?
Yeah, I should have been more careful with that as well. It depends on. Let me see. What does it? It depends mostly on the. It basically depends a bit on the surface tension of the material and the strength of the material, the strength of the bulk material, let's say. So in metals that have strengths on the orders of hundreds of megapascals, and they have surface tensions on the order of 1 Newton per meter or so. In that case, I would say that the Laplace pressure is not very important for anything bigger than 10 nanometers or so, because it's going to create a change of only a few megapascals. But for a material that's really soft, like a soft gel, its strength is only kilopascals, let's say, or a hydrogel, then the Laplace pressure is still really important even for micron-sized voids, because it's going to create a kilopascal or maybe 1 megapascal perturbation. Yeah, so it depends on the material. So for gels, I would say 1 micron. For metals, I would say 10 nanometers.
Okay, so the next question will come directly from Yupeng Zhang, who's going to ask via his own mic. Yupeng, go ahead.
Okay, thank you. So actually, I got a couple of questions, but this should be quick ones. So first, it's very simple. Is that I did not quite understand the XT curve that you showed just now. I just got lost. If you can really quick go there, and so basically that it's as simple as there are two wave planes go to a different direction, and then there's some reflection. But I see for one wave plan there are 2 reflections. I did not quite understand it. Yeah, if you can, as you can see, right. The first 2 lines we got B point, and then from the B point we got 1 reflection,
Right,
But,
right.
but for the left one, there are two. It seems one is for F and one is for C. And could you please explain this part? Thank you.
Yeah, that's a good question. Yeah, I kind of skipped through that quickly. So the way that nonlinear elasticity or nonlinear bulk modulus, basically the nonlinear bulk modulus of materials dictates whether a wave will sharpen up or whether a wave will spread out. Okay, and so what happens in most materials is that as you compress them, maybe all materials essentially, as you compress them, you are bringing the atoms closer to one another, and that tends to make the material stiffer. So you take a metal and you compress it down, and it gets stiffer, and it gets stiffer and stiffer and stiffer, and it becomes harder and harder to compress the material anymore. I think you guys had a seminar on this earlier in the summer where there's a maximum compression rate that you can apply to the material, regardless of the pressure that you apply. And then the opposite happens in tension. So in tension, the bulk modulus will decrease as you stretch the material because you're taking the atoms and spreading them farther apart. Okay. So how that plays into waves is that the wave speed is the square root of the stiffness divided by the density of the material. Okay. So if the stiffness of the material is increasing as you're compressing it, then that means that every time I increase to more and more compressive stress, the bulk modulus is going up, so the wave speed is going up. So you can see as a wave comes by, right, it first needs to take you from 0 stress to, let's say, 1 GPa, and then 2 GPa, and then 3 GPa, and then 4 GPa. So those ones that are at higher compressive stresses have higher bulk modulus, so they have higher wave speed. So the stuff that's behind tends to move faster, right? And so it will catch up to the front. And that's what makes a very sharp shock wave. And this is true for both fluids and solids. It doesn't matter. It's the same for fluids and solids. And so that material that's being compressed at the highest pressures is moving the fastest. And so it will catch up to the material that was loaded first, and then it can even overtake it. And then that's what can give you a very sharp single shock wave in compression. So that's why on the XT diagram, I draw it as just one line, because in an idealized sense, it's happening almost instantaneously, right? And then on this diagram on the far right, it's almost vertical because it's happening almost instantly. This is still a little idealized. Whereas when you release, it's the opposite. So when you release, you are taking material that's highly compressed, and that is what's first being released. So you're going from 10 GPa compression down to 9, and that's the fastest wave because it was at the most compression. So it runs away first, and then the packet that comes from 9 to 8 moves a little bit slower, and then 8 to 7 moves a little bit slower. And so all those packets are moving at slightly different speeds, slightly slower speeds. And so they spread out. And so that's why we call it a rarefaction fan, because as it releases off, it spreads out. Okay. And so that's why when we come with the release waves off of point B and off of this point over here, that's why we spread out like that.
Okay, thank you.
Point F was just indicating when you get your first void nucleating or your first crack nucleating or first damage nucleating. That's going to create a signal, and then that signal will propagate to the surface at the wave speed. It will create a signal that you can measure on the surface.
Okay, thank you so much. Very, very clear. Okay, thank you. And also another question is that it seems that the configuration of this or say ballistic test is very similar to the indentation test. So and okay, and so from the equilibrium equation, I say principle of virtual work, aspect is that we consider the initial term, so we got this result. And also there's one major factor is the interaction between different wavelengths, and that is usually it's because of the reflection due to the finite size of sample. So for example, if we consider a half space of material and we do this ballistic test, so is there any similarity between indentation solution to this ballistic test solution regarding the deformation field, stress strain, or something? Thank you.
Yeah, the long time scale solution of the ballistic problem, it should approach the Hertzian solution eventually, if it's an elastic impact. But in the short times, things are quite different.
Because of the wave.
Yeah, because of the wave propagation. I mean, even the stress state itself and the strain state itself is quite different. Like I was saying, it's mostly a uniaxial strain condition, which is not what you have in Hertzian contact. But after I have enough interaction with the boundaries, it will slowly converge with the Hertzian solution.
Okay, thank you.
Yeah.
And also one more thing regarding the number of spots, also the number of fractures, because for the experiments and also the video you just showed, usually we saw one main fracture. So is there any relation between the number of fractures or usually just one main fracture for one?
Yeah, that's a good question. You can have multiple fall as well.
Is that due to some specific parameter settings, or it's just a natural thing that you have multiple?
Yeah, if it's a very overdriven situation, then you could have multiple spall.
And that multiple spot, is that because of the multiple interaction between the stress to cause tension and for at different places, so that we got different fractures? Okay.
Right. Yeah. There's going to be more wave interactions coming off of. I'm not drawing them obviously, but there will be more wave interactions coming off of the spall plane and coming off of this free surface. And if it was sufficiently energetic impact, then the wave interaction could cause a second spall plane here. It will create another tensile region. It's just a matter of if the tensile region can reach the threshold to activate the damage or not.
Okay. Thank you. And sorry for too many questions. So one more thing is that because I saw the picture you just showed, the residual surface profile sort of the specimen are usually have significant pileup. So, but just now you mentioned like materials such as hydrogel, this thing are quite different. So, do you see or expect any sinking of the residual shape of the material after a ballistic test to be sinking shape?
To be a sink-in shape? Are you talking about the crater?
Yeah, because as you show the picture, there's significant pileup, and that's natural. I can understand that. But for indentation, sometimes for certain material, we got sink in. So I'm just curious about if there's any for for the soft material, for the elastic dominant. Of course, it's not an elastic dominant process, but if there's any scenario that we may create a sink in. Right. Fine. There's significant pileup. Yeah.
You're talking about this one on the top?
Yes.
Yeah, I actually, let me put you in contact with one of my students, Yuan Ji. If you send me an email, I'll put you in contact with him. He's doing some ballistic impact into hydrogels, and then he's been seeing some of the things that you're talking about.
Okay, great. Sounds good. Thank you. Yeah, I will email you later. And
what's cool about the gels also is that you can get kind of a bubble that forms behind the projectile as it's penetrating through. That's that you can see, and then sometimes there's a pinch off of that bubble, and sometimes there's not. And Yuan has been working on all those aspects.
Okay, thank you. One.
Okay, we're going to stop here. So, does anybody else have any questions at this point? If not, then I would like to thank Justin one more time. I would like to remind everybody that our actual last meeting for this entire summer school will take place this Thursday, when we will have a review session to cover the topics that Justin addressed today. And I'm told that Justin will be sending me also a file with some sort of very simple problems to reinforce the ideas that he explained here. And I'll send that file with my email announcing the recording of the current session. All right. Well, thank you, everybody, and see you on Thursday.
Bye.